Okay, so we left off last video talking about the third optimization in data parallelism, but now we're going to be starting a new chapter in this series, and this episode may be slightly longer than the other ones, but that's just my guess. There is going to be some technical information, but we'll explain it part by part. So let's begin by revisiting the global batch size. So we can actually update the equation with the newly added data parallelism term and combine it with the gradient accumulation such that the global batch size equals the mini batch size times the gradient accumulation steps times the number of GPUs that we have. So DP literally just means the number of parallel instances used for data parallelism. So a fancy way for saying GPU. And what's interesting here is that given a targeted global batch size, we can trade gradient accumulation steps for data parallelism to speed up trading. What does this mean? It is to say that, for example, if we run 2 gradient accumulation steps on every single GPU, well, each batch will be able to train on double the data. But instead, if we double our GPUs and reduce down to 1 gradient accumulation step, then we still have the same amount of essentially tokens being processed in each batch. However, it's done in one pass as opposed to 2 passes if we have 2 gradient accumulation steps. And this literally just means that we would take a factor of 2 from gradient accumulation and move it to DP. But of course, this means you have to double your number of GPUs, which is non-trivial. Most of us are GPU constrained, so that's why gradient accumulations are useful. But this is just a aside. In practice, people tend to maximize the number of DP nodes over gradient accumulation as much as possible since it's inherently parallel, of course. DP literally parallels in the name. Unlike the sequential nature of gradient accumulation, where you need to run 1 gradient accumulation step and then after that, second, third, and just consecutively reduce them, okay? And gradient accumulation is then added on top of data parallelism to achieve the target global batch size when scaling data parallelism alone is not sufficient before you run out of GPUs. So we will discuss this in the section right after here. One thing though is that this Simon Bohm article is excellent, so definitely read this if you're interested in data parallel training. Being able to distribute the training over different samples gives us a first dimension of parallelization, thus making this 1D parallelism, and we'll get up to 5D parallelism in this playbook. So this playbook is really long, and we've achieved 1D parallelism through just adding GPUs, but we have 4 more dimensions to cover. And in this section, we're going to go over some of the formulas to give an example and make it so that this is just not a foreign formula. Okay, first we're going to summarize, though, what we've done in the 1D parallel training with a kind of example data parallel steps setup. So we need to first determine our best global batch size in tokens. So global batch size in tokens, GBST. And this is either done by looking at the literature, looking at papers, or just empirically finding out what is good and measuring model convergence. For instance, DeepSeek and Llama models are trained with a 4K token sequence at the beginning during pre-training, but then this is gradually increased throughout in order to allow the model to actually handle large input token sequences in inference time. Anyways, the reason that 2 to 8K works well for pre-training is that documents that are longer are very rare on the web. So this is also something like 8K tokens is a lot of tokens. So unless you have like a book or something, then yeah, you won't really find like a single corpus which is longer than that. But let's get back to what we were talking about here. In essence, we select the sequence length for training, and this is kind of what I just talked about here. 2 to 8K tokens works reliably well for the evaluations we have today. And yeah, they just say that they're not going to talk about the specific training recipes and the token lengths and essentially tapering the token length to be larger at the end of the pre-training round, but we're still going to get a high-level image of what's going on. So we now know the batch size, global batch size. I'm not sure why they put it as batch size and then abbreviate it as GBS. This is kind of confusing, but global batch size is what we're talking about here with GBS, just without the tokens. And here we have another ambiguous term, MBS, but it doesn't mean mini batch size. In this time, we're talking about maximum local batch size. So what this means is that we want to find the mini batch size that is the largest possible that will not lead to a memory overflow. So literally they say here, we find this maximum local batch size on a single GPU by increasing the local batch size until we run out of memory. And finally, we determine the number of available GPUs for our target data parallelism. And then the ratio of GBS to DP gives us the remaining number of gradient accumulation steps needed for the desired global batch size. If the gradient accumulation ratio is lower than 1, which means that we have too many GPUs, because if you have a gradient accumulation step lower than 1, this essentially means that you're doing less than a full forward pass, which has no meaning because you need to do a full forward pass in order to get the loss, okay? So in this case, we can either choose to not use all our GPUs, so literally turn off some GPUs, or explore increasing the global batch size. This is one option. Another option is to test if a lower mini batch size will speed up training. So in essence, we're saying that for each GPU, it will process less data, which means that we will have a lower GPU utilization rate, but it will be faster since, of course, doing less data processing is inherently faster. But what happens here is that we're prioritizing throughput over individual GPU compute efficiency, meaning using a smaller mini batch size than possible in order to speed up training. So we could increase the MBS, but we're decreasing it on purpose to sacrifice efficiency for speed. And now we're going to talk about an example. I'll also highlight my example here on the side, but let's talk about theirs first. So they say that we want to train a recent model with a global batch size tokens, GBST, because it's in the units of tokens here, of 4 million and a sequence length of 4,000. So what this is saying is that we will need 1,000 in the naive sense where we don't have any gradient accumulation steps. We will need 1,000 GPUs in order to process at every iteration, like every full forward backward, 4 million tokens, right? Because if we have 1,000 devices and 4,000 tokens processed through a device, then we will have a global batch size of 4,000 times 1,000, but this does not account for gradient accumulation. So in this case, gradient accumulation would be 1. Let's see what they say here. They're saying that our batch size will thus be 1,024 samples, and this makes sense. And it's not 1,000 exactly because they literally say it here, we pick the closest power of 2. So in this case, our global batch size in tokens would actually be 4,000 times 1,024. If let me see if I can do this in my head quickly. That would be 4,096,000, if I'm not mistaken. So a bit more than 4 million. But let's see what they say here. Let's assume we observe that a single GPU can only fit 2 MBSs in memory, and therefore we can do 8,000 tokens per batch on a single GPU. So that is to say that each GPU can run in parallel 2 forward and 2 backward passes. So what this is saying is that we can instead, run 8,000 tokens, an 8,000 token sequence length on each GPU, so 2 training runs. Okay, and this means that with 4 gradient accumulation steps, we'll achieve our goal of 1,024 samples or 4 million tokens per training step. And I'll do this calculation with you guys here. But the next thing they say is, now what if we suddenly have 512 GPUs available? Well, in that case, we can achieve the same global batch size and identical training by keeping the minimum batch size equal to 2 and setting gradient accumulation steps to 1. So gradient accumulation steps are set to 1. We have a minimum batch size of 2 per GPU, so 8,000 tokens per GPU and 512 GPUs, 8,000 times 512, around 4 million. And if we look at the previous example where we have 4 gradient accumulation steps, in this case, we will need, 4 times 128, which gives us also 512, and then we multiply by the 8,000, which is from 2 times 4K to give us 4 million. So in essence, we're just kind of playing with this formula up here. And then in my example, I say that global batch size equals mini batch size times gradient accumulations times the data parallelism. And in this case, I'm assuming that our maximum local, sorry, I forget what this is called. It's kind of a weird name. Maximum local batch size is just 1. So we're just running 1 mini batch through each GPU. In this case, each mini batch is 5,000 tokens. And we have a global batch size of 40,000, which is much less than the batch size here, which was 4 million. So if we have a global batch size of 40,000 and a mini batch size of 5,000 with 4 GPUs, then can you please tell me how many gradient accumulation steps we'll need to do per GPU to achieve our global batch size of 40,000? In this case, it's 2, because 5,000 times 4 is 20,000, and we need to multiply by 2 to get to 40,000. So now you can see a bit how we set up a training run in terms of the hyperparameters for batch size as well as gradient accumulations. The note here is that if there are more than 512 GPUs, and depending on the network used, the communication operations will start to be bound by something called ring latency, which is the time required for a signal to propagate once around the ring of the devices. And this means that we can no longer fully overlap the data parallelism communications. This will decrease our compute efficiency and hit our throughput. In this case, we should start exploring other dimensions to parallelize on. So since we are depending on performing these data parallelism steps in between each layer in our training steps, if there's too many GPUs, this means that essentially they cannot communicate in time. Of course, increasing data transfer speeds between GPUs would make this number larger than 512. Actually, this paper was released in March, so maybe it's already surpassed that quantity. And with NVLink 5.0, which is 1.8 terabits per second, maybe this has been surpassed. But in any case, there is a limit where you will no longer be able to communicate in time all of the gradient or parameter data between the GPUs, meaning that there's other parallelism practices that need to be adopted. So what does it say here? While DP nicely overlaps the all-reduced gradient synchronization with backward computation to save time, this is to say that during the backward pass, we have the all-reduced gradient synchronization. This benefit starts to break down at large scales, like the note says here. And this is because as we add more and more GPUs, the overhead of coordinating between them grows significantly and the network requirements are become too large. For the benefits, And as a result, our setup will become less and less efficient with each additional GPU we add to the system. Another typo here. Okay, they do also provide this nice little graph, and I will explain what's happening in this left and right figure. So we see that above some limit, our throughput starts to drop quite significantly while the memory usage per GPU stays constant and is not affected by adding more DP ranks. This is to say that we have our throughput tokens per second per GPU here, and the number of GPUs. And as we increase the GPUs, it's showing that the throughput is decreasing due to the communication overhead, whereas the memory usage per GPU is actually constant. So this is to say that it's not like we're decreasing throughput while also decreasing memory requirements, but the memory requirements are literally standard and our throughput is decreasing. So, and we just covered why this is the reason, because of the communication bottlenecks and the ring latency. Here we say data parallelism is the first simple strategy to scale training across more GPUs, and this technique works like GA, gradient accumulation, but instead of parallelizing or having a single GPU accumulate mini batches, we spread the mini batches across more GPUs. And this technique, this is literally what I said, and the benefit is increasing throughput. One thing that you may have noticed is that this assumes that we can fit at least one input sample forward pass, which is to say we have a maximum local batch size of at least one into our GPU memory. Of course, if it's less than one, then we need to decrease our batch size. And this is literally not always the case. So if you have a really large model and you have a really large sequence length, well, that's going to take a lot of memory. So as we can see, larger models don't fit into a single GPU, even with activation recomputation. So if we look at here, we have the memory requirement, which I believe is 80 gigabytes of VRAM. And I think this is like the memory of A100 or H100, I forget which one. And this is just saying that, well, as soon as we get past 8 billion, then we can no longer fit a single batch size onto the GPU during training. And on 70 billion parameter models, we literally don't even have the other things on the graph here. It's just parameters. So this is quite incredible and means that we will need to have better techniques for memory usage. So the other solutions that we'll be discussing involve either moving tensors to the CPU or splitting the weights, gradients, optimizer states, etc. across GPU devices. So these are two different techniques which we will discuss in future videos. And the two main approaches to splitting are parallelism, which is in referring to the tensor, context, or pipeline parallelism, and sharing, which the techniques are called deep speed zero or PyTorch fully sharded data parallelism. These are kind of the same thing. Both approaches are orthogonal, however. So sharing and parallelism are orthogonal, which means that they can be combined, which is great. And since the sharing paradigm is closely related to data parallelism, this is the first thing that we will investigate. And since this video has already taken quite a bit of time, I will be stopping here and see you in the next video.